Hello everyone, Mr. Hein. And now we've talked about exponential equations, we've looked at linear. Now we're going to apply this to a type of math called sequences. Now what is a sequence? A sequence is just, a list of numbers. So we're just looking at numbers, and sequences come in handy if you ever look at computer programming, right? Computers recognize a lot of numbers and we make sense of that. Now there's two types of sequences that you need to know about in this class. Type number one are called linear sequences, and type two is called geometric sequences. Now, linear sequences those are numbers that change by addition. And I'll put slash subtraction because subtraction and addition are hand in hand, inverses of each other. Geometric, on the other hand, my dog scratching himself, are numbers that change by multiplication or division. Okay. So, say for example, linear would look like, 2, 4, 6, 8, 10, and so forth, where it's changing by plus 2. That's a linear sequence. Geometric would be something like 2, 4, 8, 16, 32. Well, notice it is timesing by 2. And that's geometric. Okay. Subtraction, if we said like 10, 8, 6, 4, 2, 0, a lot of you will say minus 2, and that's fine. But what I'd encourage you to do is think about it in terms of addition. Minus 2 is the same as saying plus a negative 2, plus a negative 2. Might help us when we write the equation per se. And same thing over here if we looked at, say, division, where I do 100, 50, 25, 12.5, and so forth. Hopefully what you see is that it's dividing by 2. It's getting cut in half. Well, dividing by 2 is the same as times 1/2, times 1/2, times 1/2, where those are the same thing. Okay. Now, with linear and geometric, those are sequences, just lists of numbers. A lot of what we've done. What you might notice is that when we talk about adding and subtracting, well, really this creates a linear equation. All right, where the equation is going to be t of n, and they don't use y. So I know we're used to using y. This is the same as y, just a different language that they use, where t is like the term and the n represents the number. And then what it is it's the starting value plus the rate times n. Right? Kind of like what we've been doing for a long time. So if I was to look at these two up here, this one up here, its equation will be t of n equals. Now, a lot of you, this is a mistake that people make, is they say, okay, the starting value is 2, and it's saying plus 2n. And typically that would be right, but in this case, that is actually incorrect. And the reason for that is when we talk about sequences and lists of numbers, this right here is considered the first number, and this is considered the second number. And remember that when we talk about a starting value, the starting is always at 0. So the idea of sequences is there's no such thing as the 0th number. So they always start sequences at the first number. So to get the 0th number, you actually have to work backwards to figure out what that is. So if we work backwards and you minus 2 here, the starting number here would have been 0. And then the pattern or the rate is plus 2n. And there's the equation of this one. Same thing right here is it's going to be t of n is equal to, and you'd say, okay, what's the first number? It's not 10 though, right? 10 is the first number. If I want the 0th number, I have to work backwards always, in which if I see the pattern of going 2, 4, 6, 8, 10, I'll see that it's 12. So it's 12 minus 2n, or plus a negative 2n if you want to write that. And that's the equation. The reason this sometimes is called the explicit equation, that's the language that they always use for this, is because we can find any term exactly. Explicit is like if we want the 5th term, we can find the 5th term, where we'd say, okay, if I asked you, okay, here's a sequence of numbers. This represents this sequence of numbers, 12 minus 2n. Well, if I ask, what's the 100th number? Like, what's this going to be 100 numbers from now? Well, you can just plug 100 in and say, okay, the 100th number is going to be 12 minus 2 times 100. Do the math. That gives you 12 minus 200, which is negative 188. And there's your answer. And that's why the explicit equations are nice, is because you can explicitly determine any number in that sequence forever, right, by just plugging that number in to n. Right? Now, geometric is not any different, and it's not something brand new. I think the only real new words are the words linear and geometric, okay, is that this, notice how it's timesing or dividing, this creates an exponential equation, where exponentials are the same thing, where it's going to be t of n equals your start times your rate to the power of n. Okay. So if I looked at these two problems, timesing by 2, this example here would be t of n is equal to, what's my starting value? Remember, it's not 2. That's the first number. We always need to start at 0. So you work backwards, divide by 2, and that would be 1 here. So it's going to be 1 times 2, and I'm just going to use parentheses, to the nth power. Okay. And then the second one here with division, sorry, I didn't mean to put 2, I got distracted thinking that was number 2, is going to be t of n is equal to, well, if we work backwards here and times by 2, that would be 200. So the 0th term is 200 times 1/2 to the n. And again, that's why I like to write things in terms of multiplication, because it's easier to put that in there. Okay. So there's linear and geometric. We'll look at 3 more examples to help you see it. I know the light's coming in right now, so hopefully I can get through this before it gets too difficult to see. Which type of sequence is it? Linear or geometric? Right, it's explicit equation. All right. So this first one, we look at it and we say, okay, what's the pattern? And maybe if you don't know the first two, look somewhere else. So I know that 2 plus 6 is 4. Does that keep working? And yes, it does. So it's adding. That means that it's linear. And then I could write the equation of the starting value, which, careful, it's not negative 2. Negative 2 is the first number. So you have to go backwards, in which if I went backwards in minus 4, I'd be at negative 6. That's my start. Negative 6, and then it's plus 4n. This next one here, I look at this and I say, okay, plus 2, well, it's not addition because plus 2 doesn't work anymore. Maybe let's try multiplication. 1 times 3 is 3. If I keep timing by 3, that does work. So this one is geometric because it's multiplication. So this equation is going to be t of n equals the starting value, which again, we have to work backwards to get the 0th value. So we divide by 3. 1 divided by 3 is 1/3, or 0.33 repeating. If you put that in a calculator, it won't matter. So it's 1/3. And then the pattern here, which is timesing by 3 to the nth power. And there's geometric. And then the very last one, 1, 1, 2, 2, 3, 5. This one's interesting. I see plus 0, plus 1, plus 1, plus 2. So it's not linear. Those aren't the same. If I tried multiplication, multiplication doesn't work either. Multiplication doesn't work. So in this case, it's neither linear nor geometric. This has a special name called the Fibonacci sequence, but that's unrelated. Nothing you need to know there. Okay. So there it is. Talk about sequences, a few new words for you. Hopefully that makes sense to you, and it kind of combines what we've been doing with exponential and linear. All right, good luck.